Good morning, and welcome to the second of two videos on measures of central tendency. In this video, we're going to talk about normal distributions and then conclude with some calculations using a data set that you are familiar with by now. Let's start with a discussion of normal distributions. All right. Remember that a normal distribution is one where you have frequency on the y-axis and the scores on the x-axis, regardless of what those scores happen to be. And a normal distribution is a bell-shaped curve that goes up and then down, and it's supposed to be symmetrical on both sides. All right. Again, my art skills are not wonderful, but you get the basic idea. But the key for a normal distribution is that in this particular case, the score right here at the peak, come on now, please. So right here on the x-axis, that score is equal for all three measures of central tendencies. And so the mean, the median, and the mode are equal to that score. All right, they all equal the same value of x. So it's the average score, it's the most frequently appearing score, and it's the score right in the middle. And you'd be amazed at how many natural situations and scenarios actually provide normal distributions. All right, this is, believe it or not, a very common image of what a data set will look like. All right, lots and lots of scores that are going to be clustered toward the middle, all right, and therefore high frequency up here, and then a couple of scores that are very low and a couple of scores that are very high on either side of that. But they, quote unquote, average out. All right, and that's what makes this a normal distribution. However, there are cases where there are a few outlying values, a couple of very, very low scores or a couple of very, very high scores. And what those scores do is they change the value of the mean to either a higher or a lower value, but they leave the peak where it was. All right. Now, of course, the peak of any graph like this, any frequency graph, is going to represent the mode, right? Because the frequency is the number of times a particular score appears. So the highest point is always going to be the mode. But if you have some very, 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 very low scores, that's going to move the average this way. And if you have some very, very high scores, that's going to move the average this way. All right. And so let's take a look at that. In the graph that's shown on the left-hand side, you notice this is not a normal distribution. It's not symmetrical on either side of the peak. All right. However, notice that in this case, the mode is still the highest point, right? This is the most frequently appearing score. However, the average has moved toward the right because there are some very high scores. All right, we have a few very high scores. And what that does is it makes the average, the mean, bigger than we would have expected. All right, and so we refer to this as a positive skew because we've increased the value of the mean. Okay, and the median, generally speaking, falls between the mean and the mode. Okay, so the mode is still the most frequently appearing score, but the average, the mean, has moved toward the positive side. Okay, now on the right-hand side, we've got a negatively skewed graph. All right, again, the mode is still the most frequently appearing score, but because we have a few very low scores, what that does is it moves the mean value to the left. Okay, and so we call this a negatively skewed distribution. Okay, and so that's the difference between a normal distribution and the skewed distributions. Okay, now this little section of chapter 4 is really not about measures of central tendency. This really talks about deviations around the mean, which is really the topic of chapter 5. But it's good to introduce it here because these deviations are actually calculated using the mean value and all of the individual scores in a given data set. All right, so here we're going to talk about deviations around the mean. Okay. Now, let's say that we have a score of a set of scores that consists of 5 numbers: 1, 2, 3, 4, and 5. All right, a very quick calculation here is going to tell you that the mean value is 3. Okay, because 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. Divide 15 by 5 scores, and you get an average of 3. Now, what's the deviation of these scores from the mean? Okay, well, in this particular case, the deviation of 1, 2, 3, 4, and 5 is going to be x minus the mean. And so in this case, it's going to be 1 minus 3, which is going to equal negative 2. 2 minus 3 is going to equal negative 1. 3 minus 3 gives me a deviation of 0. 4 minus 3 is going to give me a deviation of positive 1. And last but not least, I'll try to squeeze it in here. 5 minus 3 is going to give me a deviation of 2. All right, so 1 has a deviation of 2 from the mean, negative 2. 2 has a deviation of negative 1 from the mean. 3 has 0 deviation from the mean. 4 has a deviation of positive 1. And 5 has a deviation of positive 2. Now, when you use the mean to predict scores that you expect to come in from future experiments or whatever it is, this difference, x minus x bar, indicates the error in your prediction. Okay, x minus x bar indicates the error from your prediction. Now, one of the things that I do want to point out here is that if you've calculated your mean correctly, and I believe we have, right, the mean of this data set is 3, and then calculate the scores deviations, the sum of the deviations around the mean always equals 0. Now, what do I mean by that? All right, let's go back. What's negative 2? Come on now. Negative 2 plus negative 1 is negative 3. Plus 0 is negative 3. Plus 1 is negative 2. Plus 2 is 0. All right, and so the sum of all of those deviations is 0. And so the sum of the deviations around the mean always equals 0. So that's one thing that you could do in order to check that you've calculated your mean value correctly. Okay. Now, what does that sum equal to? Well, remember that in the beginning of this chapter, we defined this Greek letter sigma as meaning the sum of. All right. And so in symbols, the sum of the deviations around the mean is the sum of x minus x bar, and that always equals 0, right? And so that would be, what did we say it was? Negative 2 plus negative 1 plus 0 plus 1 plus 2. And when we added them up, we got 0, because that is the sum of all of the deviation values here. And this will be true always whenever you've calculated the deviation, the sum of the deviations around the mean, it will equal 0. Okay, always. And so that's a useful little tidbit of information that you can keep in the back of your head and take to the next cocktail party that you attend. All right, because you always talk about the sum of deviations at cocktail parties, right? All right. Anyway, so that's where we are. Now, from there, let's go back and we'll skip the deviation. We'll move away from the deviation bit for a minute and talk about what statistics actually are. Remember that a statistic is a calculation using a sample of a population, right? You don't actually interview every single person on the planet, all right? You pick 1,000 people out of 7 billion and use that to calculate the average value, the mean value. However, if it is possible to calculate the population mean, then we use a different symbol so that people who are reading your research know that you did actually interview or measure or quantify somehow every single data point in a given population. All right, and that the method for calculating this, of course, is exactly the same as calculating the X bar, right? The X bar formula is the same, right? That's equal to sigma X divided by N. But this time, this N refers to a sample of a population. In this case, because I'm calculating this Greek letter mu, right? It's kind of like a cross between an M and a U. It's mu, all right? Almost like the sound a cat makes. But this represents the number of individuals in a population, all right? So the whole population. So you have to be careful that you define whether you're talking about an entire population or just a sample of that population. Okay, if you interview every freshman at Siena College this fall, all right, that would be a population. If you only interviewed the HEOP freshmen, that would be a sample of the population. Make sense? Okay. All right. So how does this all affect our research? Okay. Well, remember that scientists and social workers and pretty much anybody who's doing research on anything that requires some kind of numerical data will have to summarize their research somehow. And this is why we do statistics. All right. And so what you need to do here is to collect your numerical data in a data set and then analyze it, all right, in order to describe the data itself and possibly to make inferences. In other words, draw conclusions about a cause and an effect here. And this is what we refer to as summarizing your research. As you'll learn in science, every study, whether it's scientific or sociological or whatever it happens to be, is you're required to summarize your data somehow. All right, and so the way that we summarize experiments is by computing the mean of the dependent scores in each condition. Okay, so we summarize the average value here, all right, the mean. Now, and from each condition, all right. Now, the conditions could be experimental versus control. All right, you give, you have 20 patients with a certain disease, and you give 10 of them a medication that you think will help cure them, and you give the other 10 a placebo, a sugar pill, and then you average those two values, the two means from each group, and then compare them. Okay, and that's then whether or not we have a relationship. And a relationship is present if the means from two or more conditions, so it could be the medicine all right, versus a placebo. Oops, that's an E right there. All right, a placebo. And so, the 10 of the 10 patients that got the medicine, 7 of them recovered from their disease. Of the 10 that got the placebo, only 2 recovered from the disease. Now, you may look at those numbers, and say, "Oh, well, 7 out of 10 is much better than 2 out of 10." But in order for science and experimental results to be accepted, the two means have to be compared statistically. All right, and most statistics will take into account things like the random sampling, the number of individuals in each group, and so on and so on and so on. Now, once you've calculated all of these things, all right, you oftentimes will represent your data pictorially, all right, in a graph. And so when a line graph, or you make a line graph, when the independent variable is an interval or a ratio interval, all right, and so this is a common method, all right. In this case, we have intervals. It looks to me like we have intervals of 5 here. And so I'm not sure what this is supposed to be. This is a list of words or maybe numbers, whatever it is. The length of the list is on the x-axis, and the recall, this is how many of them people remember after an hour or whatever time period has passed by. All right, and 5 people are able to remember 3. All right, 10 people are able to remember 6. 15. I'm sorry. Start that again. 3 people are able to remember 5. 6 people are able to remember 10, and 9 people. Oh no, these are errors. I apologize. Let me start this one more time. 3 people made 5 mistakes. 6 people made 10 mistakes, and 9 people made 15 mistakes. All right, and so we're just comparing the data here and here. Whoops, I missed. Sorry, and here. All right, and so this is an interval data set, right? Because we don't have any values between 5 and 10 or between 10 and 15. All right, and so this is an interval variable. All right, but that's an example of when you might use a line graph. Bar graphs are created when the independent variable is nominal or ordinal. All right, now in this particular case, this is a nominal independent variable, college major. Okay, and of the 24 people on this list, 8 of them chose to be physics majors, 4 of them chose to be psychology majors, and 12 of them chose to be English majors. All right, now. Actually, I made a mistake again because this is mean recall errors as well. And so what this shows is that the number of errors made by an average physics major is 8. The average number of recall errors made by a psychology major is 4. And the number of recall errors made by an English major is 12. All right, that's what we're looking for here. But again, the majors themselves is really the important point on this slide, because what it's showing is that the groups of the independent variable are just names, physics or English or psychology. All right, and that's when you would create a bar graph. Now, once you've done this, the most important thing that you can do is to compare the groups. You could compare the physics majors versus the English majors, for example. And in order to do this, what you do is you compute the sample mean from each condition. So the conditions would be physics majors, English majors, and psychology majors. Okay? And then you would perform the appropriate inferential procedure. What that means is you choose the right statistical test. All right, and there are lots and lots of different statistical tests that you can do. You have to choose the right one, and we'll get into how that happens later in the course. You're then going to once you've performed that calculation and you've gotten your results, you're going to then infer a relationship, envision the relationship found in the population, all right, from a sample. All right. So you interview all of the HEOP freshmen, and you ask what kind of music is their favorite, and of course they all come back and say country western music is their favorite music, and so you can infer that the population of freshmen at Siena also really enjoys country western music. Okay. Now, is that true? Maybe, maybe not. It depends on whether the HEOP freshmen truly represent a random sampling of the freshmen at Siena College. All right. I'm not convinced that would be a valid study, but that's the idea. All right. You're taking a sample of the population and you're using it to infer something about the entire population. Okay, so this data set is one that we've seen before. Okay, I'm gonna make a very quick little frequency distribution here on the side: 17, 16, 15, 14, 13, 12, 11, and 10. Okay, and if you recall, there was in terms of frequency, there's 18 scores altogether, right? 6 across and 3 down is 3 times 6 is 18. There's 117. There are no 16s. 1, 2, 3, 4 15s. 1, 2, 3, 4, 5, 6 14s. 1, 2, 3, 4 13s, 112, 111, and 110, right? So 1 and 4 is 5, 6 is 11, 15, 16, 17, 18. So there you go, all right? N equals 18. All right. Now, in order to calculate the mode, the median, and the mean, okay, we'll start with the mode because it's the most obvious, all right? But in this particular case, which score actually appears most frequently? All right, well, easy peasy, it's 6. Ta-da! All right, 6 is the mode of this particular, 14 is the mode of this particular data set because it appears 6 times out of the 18 different data points. Okay, and so it's obviously the most frequently appearing score, and therefore it is the mode. Okay, therefore it is indeed the mode. Now, in order to calculate the median, we have to do something a little different. We have to write these in order. So 10, 11, 12, 13, 13, 13, 13, 14, 14, 14, 14, 14, one more, 14, 15, 15, 15, and 15, and we'll finish the list with a 17. So now I've just written each data point, but I put them in numerical order from least to greatest. Now I'm trying to calculate the value of the median here. And so in order to do this, what I'm going to do is I know that there are 18 numbers in this data set. All right. Well, that means because it's an even number, there's no one middle number. So I have to look at the 9th and the 10th data point because those are the 2 data points in the middle. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these 2 numbers I'm going to use to calculate the median. Well, the median is simply the average of these two. So 14 plus 14 divided by 2 obviously gives me 14. All right. And so the mode is 14 in this case, and the mean is 14. I'm sorry, the median is 14 in this case. All right. Now, last but not least, in order to calculate the mean, you have to add up all of these numbers. Now, I'm not going to do this in my head here. I have to tell you already that I added up all of these scores. And so this is going to give me 246 as the sum of all of the scores. Okay, 14 plus 14 plus 13 plus 15 plus 11 plus 15, blah, 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 all the way down to the last number. If I add all of those numbers up, it gives me 246. Now, how do I calculate the mean value here? I take the 246 and I divide it by 18. Okay. All right, and 246 divided by 18 is going to be close to 14. I don't know what exactly it is. All right, but one of the slides later on will show us. All right, so here we go. Let's go back. Think about the data set that you just looked at. The mode is the most frequently occurring score. Okay, and so in this data set, the mode is 14. All right, because it's got a frequency value of 6. In other words, the score 14, we'll call it points, let's say. The score 14 points appears 6 times out of 18 in this data set, and therefore it has the highest frequency, and therefore it is the mode. Okay. Now, so that's the mode here. All right. If there are any questions about how we got that, go back and look at the data set, all right, and look at the number of times each score appears. You'll find that the score of 14 appears 6 times and is therefore the mode. Now, the median data set, okay? Now, here, we're looking for the score that's right in the middle, the one that's at the 50th percentile here, all right? So this is important. To find it, the first thing you've got to do is place all of the scores in order from the smallest to the largest. So here we've done that. This is the same data set that you saw a couple of slides ago. The only difference is that they're listed from least here to greatest here. Okay? And so what we're doing is we're looking for the score in the middle, which would be right here, but we don't have a score right there. All right, because there are 18 scores, we now have to look at the 9th and the 10th and take their average. But of course, since the two scores here are the same, a score of 14, we know that that is the median. All right, so since this data set has 18 observations, the median will be halfway between the 9th and 10th score in the ordered data set. The 9th score is 14, and the 10th score is also 14, sorry. And so we need to find the midpoint between these two scores. And so it's 14 plus 14 divided by 2, and that gives us 14. Now, if the 9th score had been 14 and the 10th score had been 15, then the midpoint there would be 14.5, right? Take the average of 14 and 15, you get 14.5. And therefore, in that case, the median value would be 14.5. Even though 14.5 is not part of the data set, it's still the median value. Okay? It's still the median value. But in this case, the median is 14, and so we're all happy and joyful with that. Last but not least, we'll calculate the value of the mean here. For the mean, we need to calculate the sum of all of the x values. And as I said, I did this on a calculator earlier rather than do it here. And it comes out to be 246. All right. So 10 plus 11 plus 12 plus 13 plus 13 plus 13 plus 13 plus, and so on, gives me 246. There are also 18 total scores in my data set, and so the value of n is 18. Well, it turns out that 246 divided by 18 is 13.7, or well, 13.67 actually. And so my average value here is 13.7. Okay? All right. So that is the end of the second of 2 videos on chapter 4. For homework tonight, I would ask that you do the applied or application questions at the end of chapter 4, odd numbers only, and we will go over them at the beginning of Tuesday's class. Have yourselves a great day, and I hope you learned something.